So in the last lesson, we were looking at these sampling distributions created from taking samples from a population. It says in the last lesson, we started to look at how the data from a group of samples taken from a population with a given proportion allows us to find a confidence interval. We are 95% sure that the same size samples, so if we're taking samples of 30, another sample of 30, from populations with that proportion will fall within the confidence interval. So if I did a sampling distribution with a 40% proportion or 0.4 proportion like we did yesterday, if I took another sample from a different population with the same proportion, 95% of the time it would fall in the interval of 95% interval on my confidence interval. Not on my confidence interval, on my sampling distribution. Lots of vocabulary. The only way to be 100% sure of the population proportion is to collect data from the entire population. Since this is usually not feasible, we use data from samples to be sure enough about information to move forward. So the question becomes, why 95%? Because it's not like a magic number. It's actually a very human decision. People had to decide, okay, what's enough confidence? It says, why 95%? We are only 95% confident. There is a 5% chance that a same size sample from a population with that proportion will fall outside the confidence interval. So one thing we could do is use something like a 99% confidence interval. So if we use something bigger like 99%, we only have a 1% chance of discluding samples that do not come from a population with that proportion. At the same time, the interval gets so big that we include more samples that do not come from populations with the given proportion. So we're trying to make decisions here, and if we make a huge interval, it almost becomes like meaningless. On the other hand, if we use an 80% confidence interval, for example, we could narrow the range of values, which would make up the confidence interval, which would give us a more specific estimate, so a smaller confidence interval. But then we have a 20% chance of being wrong. What is the balance between these two issues? Too small and too big? Both have their positives and negatives, just like most meaningful decisions in life. The percentage for the confidence interval can be different than 95%, but that is the most common choice in statistics to balance the two possible complications. It is the one we will use for this course. To summarize, inferential statistics, statistics that makes decisions, is in its essence the field of math that lets us move forward with confidence in the midst of uncertainty. That is why statistics is a required course for medical fields, business, psychology, some education courses, mathematics, etc. Data science is the area of computer science involved in writing programs to process data using statistical techniques. This is such a huge part of decision-making in the real world that data sciences can get jobs virtually anywhere. So what we're going to do is we're going to play with some factors and sampling distributions on Delta Math. So this says, as a class, use Delta Math simulation of flipping pennies activity to illustrate the following concepts. And I'm actually going to add some to this before we look at it. So what happens when we change the sample size? So we're going to do two things. We're going to do 100 samples of 10 coin flips. And we're going to, so this is 10 coin flips. And then we're going to do 100 samples again of 50 coin flips. And we're going to see what types of changes occur. Okay, so we'll write those two. So I'm going to pull the Delta Math over. And we are going to do, all the data is cleared. We're going to do 100 simulations for 10 flips. So I'm going to get 100 dots on here, okay? And we're going to press generate. So I'm just going to take a range. When I did the 10 coin flips with the samples, some of them, only 20% of them were heads, okay? And some of them, 90% of them were heads. So imagine this was our class and we were doing something with coin flips. It's just a computer can do it much faster, okay? So if I go back to my notes, we had a range. This is not a confidence interval. We're just going to try to keep things quick of 0.2 to 0.9. Okay, that's the range that I had when there were 10 coin flips per sample. So now we're going to see what happens when we do 50 coin flips per sample. So we'll go back to this. So I am going to clear for all simulations, clear the data. We're still going to do 100 simulations, but now we're going to do 50 coin flips. Okay, so I changed this factor. I'm going to generate. So now we see that this goes from about, it looks like 0.32 to, I don't know, let's say that this is 0.62. Okay, so now when we switched over to this one, the proportion went to 0.32 to 0.62. So we're trying to say what happens when we, in this case, increase the sample size. So by increasing the sample size, the range, and we can say also if we had found the confidence interval, right, decreases. Okay, so we're getting kind of a smaller confidence interval, and that's because in 10 coin flips, right, maybe something random happens. Like I can definitely see in 10 coin flips just getting 2 out of 10 of them being heads. But in 50 coin flips, to get only 10 out of 50 being heads, right? Things start, as we do more coin flips, things kind of head towards the middle or what we expect the results to be. So our next thing we're going to do is what happens when we increase the number of trials. So if we do more trials, changing this samples number over here, and the way we're going to experiment with this one, okay, we're going to do 50 samples of 20 coin flips. And now we're going to do 500 samples of 20 coin flips. So we're keeping the sample size, the 20 in this case, constant, and we're changing how many samples we get. So let's go back over to Delta Math and we'll look at those two scenarios. So let's see. We're going to clear for all simulations. It says we're doing first 50 simulations or samples of 20 coin flips. So we're going to generate this. Okay, so just kind of make a mental picture of what this graph looks like. And then we're going to do clear the data, 500 simulations for 20 coin flips. So we see it's bigger, right? Obviously, because there's more. And do you see how it has more of that normal curve shape? Okay. And that's what happens. The more samples I do, the more my graph starts to look like the normal curve, which means that my calculations are even more accurate because we're assuming that it looks like a normal curve in the calculations we do. So if we come back over here, we could say here it was more normal. And this one was a little more scattered. Okay, still approximately normal, but the one with more samples, it gets more like that normal curve. Okay, so that's for more samples, or as the number of samples increases. The curve, or the distribution, we'll say, because we didn't really have a curve there, the distribution looks more normal. Or let's write normally distributed. I think we know what that word normal means in statistics, but I want to be clear that it looks more normally distributed.